So this is going to be a video on chapter 6.3, which is basically working with the same thing we did in the last video, 6.2, but this time we're going to be dealing with situations where the standard deviation and the average isn't 0 and 1. Because if the standard deviation averages are 0 and 1 respectively, or rather if the average is 0 and the standard deviation is 1, then it becomes really simple to look up the z-scores by just looking them up in the table. But if it's different than that, and it often is, then it's a little bit more tricky, but not much. So basically, the idea here is how can we convert values from data into z-scores? Because remember, we have that z-score table, which is right here. So this is our z-score table, but it only works if we have z-scores. Like this table will not work just for any other number. Like if I asked you, what's the probability of picking somebody who weighs 162 pounds? Well, there's no 162 here. So you have to be able to take your data and convert it into z-score values, and that's what we're going to be doing with this formula right here. So this formula takes a value x and converts it into a z-score, which we call z. Basically, the way this works, and it's a very simple formula. Obviously, you can see it's not that complicated. This is the value in question, so that's the value you're looking at. This is the average, so AVG. So remember that mu there is the symbol for average, and this sigma down here is the standard deviation, which we'll call SD. So basically you take your value, subtract it from the average, and divide it by the deviation, which again makes sense because remember all the z-score is number of deviations. I'll put SD here, number of standard deviations away from mu, or away from the average. So if I say that the average, just to give you a real easy example here, if I say the average is 10 and the standard deviation is 2, and I say that I want you to check for the value, how many deviations away from the average is the value of 14. Well, without even doing this formula, you know that, okay, how many deviations away from the average is this value of 14? Well, it's 2, because it's 2 and then 2 more. So 10 plus 1 deviation plus another deviation is 14. So this would have a z-score of 2 because it takes 2 deviations to get from the average to that value. So think about the z-score is how many deviations do you need to get from the value back to the average, whether you're going up or down. And again, you can have decimal z-scores as we often do, which is why this formula is here, mainly to take care of the decimal ones. So let's put this into practice here. So assume that the weights of men are normally distributed. Okay, that's good because we have to have things normally distributed here in order for this stuff to work. The average is 162 pounds, so this is my mu. And the standard deviation, so my sigma here, is 29. So we start at 162 as the average, and then we jump 29 each time, either up or down, to get to a deviation. If one man is randomly selected, what's the probability that he weighs less than 174 pounds? So we're going to say that x is equal to 174. Now it says less than 174, but you'll see why I'm just picking 174 here in a minute. And we have that the average is 172, and that the deviation is 29. So basically we're going to figure out how many 29s does it take to go from 174 back to 172. Again, how many deviations is it to go from here to here? How many deviations away are these? And that's where we use the formula. So z-score is equal to the value minus the average, which gives us the distance, and then how many deviations does it take to fill that? And it's going to be kind of a small number here, which is fine, because remember, our z-score table really only goes up to, if you look at it, really goes up to 3.4 and negative 3.4. Well, 3.49 if you go to the end there. So our z-scores aren't meant to be really big values. They're in between basically 4 and negative 4. So if we calculate this out here, 174 minus 172 divided by 29, we get about 0.0. I'm going to round that up to say 0.07. So 0.07. So this is the z-score. Now it's asking me what the probability is. What is the probability that I get a value that's less than this z-score? So remember, your table, if I draw this my curve here, you have your average in the middle. So this is your mu. Remember, your table takes a certain value, like this one right here, takes a certain value, takes that z-score, and gives you the probability of getting anything less than that value, or less than or equal to that value. So when it's asking for the probability of weighing less than 174, it's basically asking for the probability of getting a z-score of this or less, which is exactly what my table gives me anyway. So if I go to this table here, I'm looking for a z-score of 0.07. So here's 0.0, here is 0.7 right there. So I'm going to look for this z-score right here, 0.5279. So if I go to my answer here, this would be 0.5279, which is roughly 52.79%. That is the probability of getting a value that has a z-score of less than 0.07, which by extension, if you convert it back, is the probability of picking somebody with a weight of less than 174. Because remember, 174 and 0.07 are basically the exact same thing. It's just that one is given to you in pounds, like 174, and one is given to you in terms of the standardized z-score, which is what 0.07 is. So all this formula is basically a translator. All this little z-score bit here is basically a translator of how to go from pounds to z-score. Because we don't have a table for pounds, but we do have a table for z-scores to get our probabilities from there. So this says that your z-score of 0.07 is right here, or again, a weight of 174, however you want to think about it. And the probability of getting anything less than that is about 0.52, or 52%. Which again makes sense because if you notice the way that a normal distribution works, if you remember from, that's a really terrible curve. Let me try that again. If you remember the way a normal distribution works, it's a symmetric curve that's centered about the average. So here's my average, and it's a symmetric curve that has the largest hump at the middle of the average, and then it curves off, right? So if I'm on the average, that means 50% of my data is less than the average, and 50% of my data is more than the average. That's what it means to be normal. You're centered about the average, and you have an even split. Well, if this data right here is not that far off from the average, so 0.07 is like right here, that's how many deviations away it is, even less than that maybe, then it shouldn't be any much more than 50% because I'm not that far higher than the average. If I said, what's the probability of picking somebody with a weight of less than 250 pounds? Well, that's going to be a really high number because that's going to be many deviations to the right. So less than that's going to be covering quite a bit of area there. So again, you can use some common sense checks to make sure that you're doing your work correctly. If your value is pretty close to the average, or let me put it this way, the closer your value is to the average, the closer the probability will be to 50% if you're just looking for something to be less than or more than that value. Now again, this was a less than one. Remember, your table, your z-score table here, is made for less than problems because it gives you the area to the left of the value. Or again, area means probability, so it gives you the probability to the left of the value. If I asked what is the chance that they pick somebody that weighs more than 174 pounds, then I would have to take this and subtract it from 100. So if I wanted more than 174, I would do 1 minus 0.5279, or 100 minus 52.79, whatever, and get my answer there, which would be about 48 or 47 pound or 47%. So more than, you have to subtract it from 1. Less than means just take your table and go with it, okay? Come on. So psychologist is designed to experiment, or is designing an experiment to test the new training of a program. She wants to pick people who have a IQ score between 85 and 125. Okay, so it says given that the IQ scores are normally distributed, which is good, the average of 100, which is how IQ scores are made, that the IQ score test is made to have an average value of 100, and then you're either up or below from that. Standard deviation of 15, which is also true. They're made to have the standard deviation of 15. So all this is accurate in actual life too. What percent of people have an IQ score between 85 and 125? So if this person wants to make a test to test airport screeners, and she wants to pick people that have an IQ score between these ranges here, how hard is that going to be for her? So again, this is asking what percent of people are likely to have an IQ score between those two values. Because if it's a very small percent of people, she's going to have a hard time getting her group. But let's figure out the numbers first. Now, if you remember from last video, when we're asked a between question, what we do is we find the percent that we get the 85, we find the percent that we pick 125, and then we subtract them. Because remember, once I get a percent for 85, that will be the probability of picking somebody with an IQ score of 85 or less. When I get the 125, that'll be the probability of picking somebody with an IQ score of 125 or less. So then I'm going to subtract them to get the probability of picking somebody that has an IQ score between those two values. So graphically, it looks like this. You have your curve here. here's your average value of 100, right? Let's say 85 is right here, and 125 is right here. So when I get my probability for 85, when I do the same thing I did in the last problem for 85, I will get the probability of picking something less than or equal to 85. And then when I do the same thing I did in the last problem for my 125, I will get the probability of picking something that is less than or equal to 125. But I want the probability of it being between. So what I'm going to do is I'm going to subtract this 85 probability from this 25 probability, and that will get me the probability that's between the two. Okay, so if I subtract this off, I'm left with what's between them. So that's the idea here with between problems. You get the probability for both, and then you subtract them together. So let's do the 85 first. Let's figure out the z-score for 85 first. So the z-score is the value minus the average over the deviation. And again, z-scores can be negative. So that's fine. If you're below the average, you have a negative z-score. So 85 minus 100 divided by 15 is just going to be negative 1 because, again, if the deviation is 15 and you're 15 below the average, that means you're one deviation away, or in this case, one deviation below, so negative 1. So let's get the probability for picking somebody one deviation below the average. So negative 1.0, which is there and there. So that'd be this one right here, 0.1587. So if I go to my thing here, there it is, 0.1587. So that is the probability of picking somebody who has an IQ score of 85 or less. All right, so now let's do it for the 125. So z-score is 125 minus 100 over 15. So if we rock that out here, 125 minus 100, divide that by 15. We get 1.6 repeating, so I'm just going to put that as 1.67. I'm going to round it off there. And it's a positive z-score. So let's go to my z-score table and do 1.67. So that'd be right here. And that's 0.9525. So I go to my thing here, 0.9525 of picking somebody with an IQ score of 125 or less. And again, if you think about it, that makes sense because 125 is almost 2 deviations above the average IQ score, which again, you would consider a pretty smart person. If the IQ score directly relates to smartness, which again, we can debate about that later, but if you have an IQ score that's really high, like 125, that's far away from the average, you're much more likely to pick somebody with an IQ score of less than that than you are to pick somebody with an IQ score of more than that. So it makes sense to have this high probability here of picking somebody with a less than 125 IQ score because there's going to be a lot more people that are less than 125 than there are going to be for a lot more people that are less than 85, because 85 is a pretty low score, quote unquote, because it's below the average and it's one deviation below the average. So there's not going to be a lot of people that are that far below the average by definition, because again, the average is the standard 50-50 score, right? So if you're below that, you're less likely to pick somebody that's even lower than that than you are to pick somebody that's even lower than the smart end. So we're going to subtract these two together, 0.9525, which again is right here. So that's the green area here, 0.9525 minus 0.1587. And we should get the area, or the probability, because they're the same thing in a normal curve, of it being between those two. So 0.9525 minus 0.1587. And we end up with 0.7938. So there's about an 80% chance, 7938, so about a 79.38. So that 79.38% chance that any one person she picks has an IQ score in the range she's looking for, which is lower than 125 but more than 85. Which again is not that hard of a thing to do. So if you have access to a large group of people, like if you're working at an airport and you're testing the staff, I'm assuming you do, it's probably going to be pretty easy to pick somebody or to pick a group of people that have an IQ score between these two values if you have roughly an 80% shot for any one person. Now, we can work these backwards as well. So by backwards, I mean they give you a probability and they want you to find the z-score that relates to that. So here is what it is in words. I'm going to actually just do an example for this. You can read this on your own if you want to pause the video, but I'm actually going to work through an example because it's usually easier to show what's happening there rather than just saying the formula verbatim. So this is what I mean. What weight separates the lightest 99.5% of men from the heaviest 0.5% of men? And we're going to assume that the normal distribution has an average of 172, so that's my mu, and a deviation of 29, like before. So if we do this graphically, and I always find it that for students, it might be easier to draw a graph when you first start these out. It doesn't mean you have to do it every single time throughout the rest of your stats stuff here, but this might help you visualize what you need to do. So this is my bell curve, a very bad bell curve, I know, but stick with me here. My average is in the middle, so this would be my 172. That's my average value. I'm asking what value separates the lightest 99.5% from the heaviest 0.5%. So heaviest would be on the right-hand side, right? Because this is the middleweight. So these are the heavyweight people. These are the lightweight people on the left. I'm going to actually smooth out the side here because that's just, well, I guess I have to erase the whole thing. Let me try this again. That was just not going to be conducive to a good drawing environment there. That's a little bit better. So I'm looking for the value. I don't know the value, so I'm going to just put a mark here and put it as question mark. I'm looking for a value that separates the lightest 99.5% of men. So the lightest will be on the left side. So I want 99.5% of men to be on this side and 0.5% of men to be on that side. I'm looking for what value does this. What value splits it so that you have 99.5% of men that's lighter than it and 0.5% of men that's heavier than it. So we basically work this in reverse because remember our formula is z-score is equal to x minus average over deviation. So I'm basically looking for the x. That's what I'm trying to figure out. What is the value that gives me this situation? Well, I know that my average is 172 minus. My average is 172 and my deviation is 29. So if I could just figure out the z-score, if I just knew the z-score, I could backwards work this problem using algebra to solve for the value. And it just so happens that I can figure out my z-score because I already have the value that's behind it. So this 99.5, if we put it into decimal form, is 0.995. This is what would show up in the table. So whatever z-score is associated with this value in the table is the z-score I'm looking for. So if we go to our table here, 0.995, remember that, 0.995. I'm looking for 0.995 in the middle here. Wherever I can get 0.995 in the middle, I'm going to backtrack that and get what z-score fits that because that's this green area here essentially. That's what I'm looking for. What value has an area of 0.995 behind it? Because remember, area and probability for a normal distribution mean the same thing. So let's do 0.995 as close as we can get here. So here's 0.9949, here's 0.9951, so 0.995 would be directly in the middle here. And that would be 2.5 and looks to be between 2.57 and 2.58, which is actually 2.575. Again, this table doesn't have the values down here, but that's one of the special values that would usually be listed in the bottom of the z-score table is 2.575 because 0.995 is a pretty common value we use as a splitter. But more on that in a later lesson. So right now, just trust me here. If it's between 0.9949 and 0.9951, and our z-score is 0.25, and then it's between 0.07 and 0.08, we're just going to call it 0.075 because that's halfway between 0.07 and 0.08. So my z-score then is 2.575, and then this just becomes an algebra problem. Multiply by 29. That's a time symbol, by the way, not an x again. Multiply both sides by 29 to get rid of the division. We get x minus 172, and then here we have 29 times 2.575, and we get 74.65. So 74.65, or 675. I saw it right, but read it wrong. We add 172 to both sides, and we end up getting, so plus 172, 246.675. So 246.675 is equal to x. And this would be the weight that separates the heaviest 0.5% from the lowest 99.5% of men. So if you weigh, I'm just going to round it up to 247. If you weigh 247 pounds, that basically means you're in the 99th percentile of heaviest men. So if you weigh 247 pounds, you're heavier than 99% of the other men that were evaluated using the standard here. So if this was men in America, you'd be heavier than 99% you'd be heavier than 99% of men in America. If this was men globally and you weighed 247 pounds, you'd be heavier than 99% of the men globally. If this was just men in Illinois, you'd be heavier than 99% of the men in Illinois. So again, you always have to take into account where is your sample coming from. If your sample is that of the world, then you can apply it to the world. But if your sample is just that of people in a certain area, you can only apply the data to the people in that certain area. And again, this formula right here, this is really, I'm going to stumble on my words here, I'm sorry, but this is really no different than what we did in the last video. It's just that now we have data that's not just centered around 0 and 1. So we have to use this little new formula here, this z-score formula. Where's my mouse? There it is. We have to use this z-score formula, which is nothing more than a basic math calculation. If I asked you how many threes are in 7, you would simply do 7 divided by 3 and get an answer. That's how many 3's fit into 7. It's going to be a decimal number, but you can do that. That's what division does. How many of this does it take to fit into that? This is no different than that question. It's just asking it in terms of a z-score. How many standard deviations does it take to fill in the gap between your value and your average? Which, translated, simply means how many deviations away is it from your value to your average. And I keep harping on that point, but that's because it's a key reasoning here, is because most people think of this z-score as this ethereal sort of weird number, and it's not. It's simply how many jumps. Think of deviation as the length of your jump, and your average is like your home base, and your x is where you're starting at. So the z-score is simply how many jumps, aka deviations, does it take for you to get from your starting point back to home base. That's all a z-score is. How many jumps, and a jump is considered the length of a deviation, does it take to get from where you're at, your value, to where your starting point is, which is your average. And again, it can be negative or positive depending on whether you're jumping back to the average or jumping up to the average, whether you started above or below. So that's it for this video. Again, hopefully this helped you out. If you need it reviewed or so, that's fine. If you need some more questions or so, let me know. Otherwise, thank you for watching. Have a good day, night, or afternoon.